Yeah. So this means that it goes from the reactant side to the product side, as well as product side to reactant side. This negative delta H means it's exothermic. The negative sign means it's losing energy. Okay. All right. So let's look at this. So how do you look at this reversal process? So there are three ways to look at this. You can look at it as reactant and product. You can look at it as heat. Yeah, this side is endothermic and that side is exothermic. And the third way to look at this equation is 4 to 2, because this is for gases. Why is that important? Because in LCP, Le Chelter principle, whenever you're analyzing a reversal process, you look at it this way. So this is for concentration, this is for heat or temperature, and this is the effect of pressure. Okay, so this is three ways of looking at the same equation. All right, so let's see. Describe and explain the effect of increasing temperature, pressure, and concentration of reactant on the yield of the reaction. So let's break the question down a bit. There are two parts to the question. One is describe and the other is explain. Describe means tell me what will happen. Explain is tell me why that will happen. Okay, so two parts, and no wonder this is a 6-mark question, which means 1 mark for description, 1 for explanation, 2 for temperature, 2 for pressure, 2 for concentration. So let's analyze it one at a bit. So we start with increasing temperature. So if I increase the temperature, now remember, we are talking about yield. Yield means going to the right. Okay, so we are looking for when does it go to the right. So if I increase the temperature, it tries to absorb that, right? So it goes to the endothermic side. So increasing temperature moves it to the left. Now what happens? So the answer will be yield goes down. That's description. Explanation. The energy supplied is being absorbed, so it moves to the endothermic side. The equilibrium shifts left because it's going to absorb energy. All right. Second factor, pressure. So let's talk about pressure. If I increase the pressure, it goes to the right side. So I will say that the yield goes up. That's description. Why? Because there are higher number of gaseous moles on the left, so they collide more, they react more, they move to the right. That's your explanation. So remember, it's the number of gaseous moles that matter. All right. Third factor. We are going to talk about this concentration. So if I increase the concentration of reactant, the reaction goes to the right. So the description is yield goes up. The explanation is that it is used, so reactants collide more, and so more product is made. That's the explanation. 6 marks. All right, question number 2. Why is the temperature kept high in this exothermic reaction? So it's important to understand why this question is so important. The temperature is kept high even though it's an exothermic process. We just talked about that if I increase the heat, it's going to go back. Yield will be lower, but for some reason, we still keep the temperature high. So there's the idea of compromise. Why? Because we are saying that when you increase the temperature, yield goes down, but rate goes up. Because rate depends on kinetic energy, and when they have higher heat, they are going to collide more, they have higher kinetic energy. So rate is faster, but still yield is going to go less. So it's the idea of compromise there. All right, question number 3. Why does the addition of a catalyst not affect the yield of this reaction? What does a catalyst do? Catalyst lowers the speed of reaction, speeds up the reaction, increases the speed of the reaction. So there are 2 reactions happening here, one to the right, one to the left. A catalyst speeds up both of those reactions. Okay, and that is why it does not affect the yield, because dono sides are increased. So product bhi zyada banega, reactant bhi zyada banega. There is no effect on the yield. Equilibrium remains unchanged. 4th, define dynamic equilibrium. Pretty standard question. You just have to remember what it is. Dynamic equilibrium is when the rate of forward reaction is the same as rate of backward reaction. So the rate of forward reaction is the same as rate of backward reaction. All right, number 5. Draw the energy profile diagram for this reaction. So how do you draw the energy profile diagram? It's pretty standard. You have an exothermic reaction. So you're going to have this graph. You're going to have a higher point for the reactant and a lower point for the product. And it's going to go like this. Now the shape can be different. Like you can have this, you can have this, but it doesn't matter. As long as you're showing an increase and then decrease, you're good to go. All right, so where's the activation energy? Activation energy is this part. And where's the delta H? Delta H is this part. Now, important bit to remember here is that activation energy has arrowhead upwards. This is the tail, okay? Similarly, delta H has the arrowhead here. Make sure that you label it and then you do not draw it like this. Like you don't have arrow with two heads. You just have one-sided arrow. And that is your diagram. It shows there is a decrease in overall energy from reactant to product. So it's exothermic. And then there is the activation energy, which is going up. Now, this question is of 4 marks because 2 marks are for what we have drawn so far. And there's another mark for the catalyzed reaction. So we have to draw another one. So in this case, you have to show that the reactant and product remain where they are. So reactant remains here, product remains here, but the catalyst lowers the activation. So you're going to draw another curve, but this time it's going to go slightly less as far as the activation energy is concerned. Okay, so there you go. This is your activation energy, and that's how it goes. Okay, all right. So that is the energy profile diagram. So while we are at it, let's talk about what happens if this was endothermic. So if this was endothermic, we will have a reactant, we will have a product, but product will be higher than the reactant. Again, the shape doesn't matter. It can be a triangle, it can be a rectangle, or it can be like this. Doesn't matter. But what matters is the direction of the arrows. So you have to show that the arrow of activation energy goes like this. The arrow of delta H goes like this. Again, the important bit to remember, activation energy is directed up. It has an arrowhead upwards. And delta H also is positive here, so it's going up. If they asked us to draw a catalyzed reaction, so again, delta H remains unchanged, but activation energy goes down. So you can see over here that the activation energy is going to go less, like it's lesser than the one before it. So this is your activation energy, this catalyzed one. Sometimes the examiner asks you questions about the reversible reaction. So if this was a reversible reaction, then this EA that I've shown in the white is basically for the forward, and this is the EA for the backward reaction. Because in the backward reaction, your product is your starting point and reactant is your ending point. The definitions of dynamic equilibrium, rate of reaction, the idea of what factors affect rate of reaction and what factors affect the yield or equilibrium. Why is the idea of yield important? Why the idea of compromise is important? So what does the catalyst do in all this? So these are the major things you need to remember for these 3 chapters.